Then we looked at methylamine. Methylamine with the methyl group here is 10 to the minus 4, about 10 times stronger. And then we went from methylamine to dimethylamine. If you go to dimethylamine, it comes out to 10 to the minus 4, 5.9 versus 4.2. So if we add two methyl groups, methyl groups being electron pushers or electron withdrawers. Yeah, methyl groups would be electron pushers. So if we have two of those, it's going to become a little more basic. And then we go to trimethylamine. When we go to trimethylamine, what do we have? Go 5.9 to 6.3, but this is 6.3 times 10 to the minus 5. And so what happened there? So one methyl becomes a little bit more basic, two methyls becomes a little bit more basic, and then three methyls, it becomes not more basic, but less basic. And so what's going on there? What's going on there? This type of stuff often happens when you're doing science. You know, all of a sudden things don't appear to give you the expected results. In Chem 4 and Chem 1A, to a large extent, you know, they just don't talk about it. The stuff that doesn't work out quite nicely is usually omitted. You know, I'll show you. There's a little tutorial posted on this on the web. You can take a look, where they say, "Oh, this only applies to this subset," but it seemed to work. You know, but something's going on here. Maybe it could be. Did I talk about this? Due to steric issues, or what do you think? What do you think that's due to? Or maybe there's some kind of hydrogen bonding issue. You know, with nitrogen now, this nitrogen doesn't have any hydrogen bonds, but the situation is we're adding a third electron pusher, but the basicity now is just dropped. And so what happened there? And so what happens is, this is what happens when people people start doing the real science. Things start to get messy a little bit. You know, if everything worked cleanly and all your experiments gave clear data that was in line with expectation, you could be done with a PhD probably in 3 years. But what happens is things don't work out so cleanly. You have headaches in your data like this. This is a headache because all of a sudden what we're thinking, you know, doesn't work out so cleanly. And so there's got to be other factors involved here if this data is right. You know, if this data is right, then we're going from ammonia to methylamine, stronger, to dimethylamine, stronger, and then all of a sudden to trimethylamine, a lot weaker, 10 times weaker. What's going on there? You know? So I was flipping through some tutorials online and saying what people do for this, and pretty much they ignore it until you have to deal with it. When you have to deal with it, then the headache, you know, to be aware of that. And so you have to be aware, like in Chem 4, they avoid a lot of reactions because they just don't want to talk about it. They avoid, so you know, you might think you've covered a lot of different reaction types. Same thing in Chem 1A, you know, sometimes they avoid. I've been trying to not avoid different reaction types. But these types of things happen, so we have to dig deeper into the structure to see, you know, what is that correlated with? What is that drop in basicity correlated with? Why is there a drop in basicity? And these types of problems we tackle by looking at the structure, you know, digging deeper into the structure. This is why we want things like Spartan to see, you know, did something happen here? And so what we should do, maybe as an add-on to this, is we should do ammonia and then methylamine and then dimethylamine and then trimethylamine and then see, is there something that happened once we went to 3 methyls? Unless can you come up with some hypothesis right now and just tell me what the answer is? You want to propose a hypothesis? No, what we do is we just look at the data, try to see, if we can find some kind of correlation. And so that's what we're doing today. What we're doing today is we're doing a series of acids, but I want to throw in this series of bases too. So we're going to do a little bit extra. Maybe we'll cut down on the acids. But what we're doing is we're trying to, this is the scientific method. The scientific method is we take observations and then we try to look for these patterns. And this is the pattern that we're looking for. So we're trying to look for a pattern for this. Sometimes these patterns, seem to work brilliantly, and then there's one that's outside. So what do you do? Well, a lot of people are tempted just to ignore that. Shoot, if I didn't do that one, everything would have worked out perfectly, right? And then some people, and this is the case in science, some people have ignored certain data points and have been called out on that, that they didn't want, like for example, there's a pretty sad story about some researchers who conveniently left out some data that didn't quite fit their interpretation, and it turned into a big scandal because these were really one of the people who signed on to that was a Nobel Prize winner, but this is the type of situation that in Chem 4 and Chem 1A and Chem 1B, people get this impression, you do this calculation, you do this ideal gas calculation, you get the right answer, and that's what we should observe, right? But then sometimes it doesn't work out so cleanly in science. And so what we do is we just do this. It's not like we have to come up with some brilliant hypothesis. We just look at the data and then try to figure it out, And so that's what science is. Science is not a genius type thing. It's just grinding through the data, and then figuring it out. And then a lot of people who make these outstanding discoveries have just done that. Not to get me wrong, a lot of these outstanding discoveries were, pretty impressive because they recognize certain things. But we'll take a look at that. Well, anyway, I want to conclude with this here, and I need to talk about the last type of acid-base reaction. And so I'm talking more about acid-base chemistry than I did last year, so the practice test isn't exactly right. And so I'm cutting out a little bit of chapter 12 to do this. But the last one is Lewis acid-base reactions. Lewis acid-base is electron pair donors, the base, electron pair acceptors, the acid. Boron trifluoride is a powerful Lewis acid. It's a powerful Lewis acid, but it doesn't have any hydrogens, so it's not a Bronsted acid, it's a Lewis acid in this case. It's a Lewis acid because it's really capable of accepting a lone pair. And so this sp3, you see the sp3 comes in here, there's an empty p orbital here, right, because this is sp2. Empty p orbital. This sp3 goes into the empty p orbital, and then it'll rehybridize this to sp3 here. Can you guys kind of see that, or do I need to write it on the board? But essentially, this would be a Lewis acid base. This is what we call a Lewis acid base adduct. The product is we form a bond between the Lewis acid and the Lewis base, and there's a covalent bond. And this covalent bond is called a dative or coordinate covalent bond, in which both electrons come from one atom, atom A in this case. Now, how do you recognize a Lewis acid? What's the strength of this Lewis acid? I said, I just told you BF3 is a strong, weak, or is a strong Lewis acid? Well, obviously it's going to be strong because it's got less than an octet. Less than an octet is probably not so happy. And it can't get an octet from fluorine. Why can't it get an octet from double bonding with fluorine? Well, yeah, fluorine just doesn't double bond because it loses electrons doing so. So, in general, here's another example of Lewis acid-base reaction. Oxide's a good Lewis base. Calcium oxide is a solid. And so sulfur dioxide is a gas. So this gas here collides with the surface, reacts with the oxide. And we produce calcium, what's this? Not sulfate. Sulfite. This is calcium sulfite. Looking at this, they maintain the octet. We could have double bonded here, got rid of one of these formal charges here, this one and this one, actually two formal charges. If we expand the octet, they left it as an octet. So calcium sulfite. This is, again, another example of Lewis acid base. This one should be a pretty decent, Lewis acid because, you know, there's a positive charge on the sulfur. And Lewis base is a negative. As long as that it's capable of accepting a lone pair, which it is, not a lone pair to form a bond, so it's sp3. This is a weird ion here. If you look at this, this is aluminum surrounded by 6 waters. But these waters actually bond. This is a Lewis acid base reaction that created this ion. This is called hexa aqua aluminum 3 ion. And this is what happens when aluminum gets dissolved in water. And so when aluminum gets dissolved in water, it forms this by a Lewis acid base reaction. Aluminum has a very high positive charge, and one of these sp3 lone pairs can come in here and bond to it. Now, when we do this, when we do these types of things, it's very strange. This is more Chem 1b here than Chem 1a. But the water, we say, retains its charge, aluminum retains its charge. So this is going to be, the charges don't add up. So we don't do formal charges for these types of species, which we'll talk about later. But essentially, this is a bond here. And the bond here cannot be described using valence bond theory. Valence bond theory fails for species like this. We must use MO theory. And so it turns out we can bond 6 of those. Now those 6 aren't permanently bonded. I mean, things can come in here and break this bond, you know. And so the aluminum can react with other species. That is, things collide with water molecules, break it off. But this one turns out to be interesting because tetrahydroxyaluminate, you know, if you look at the polarity of this bond, this is Al3+. Al3+ is going to suck electron density away from water, making these 2 hydrogens much more polar than they normally are. And so this ion here, hexa aqua aluminum 3, is about as acidic as acetic acid. This is because the waters are much more acidic when they're bonded to the aluminum like that. And so here we can see, here's one of these waters that are bonded here, and here's another water. And so this water is going to be attracted because this H is going to be quite delta plus here. And so it's going to pluck a proton off and make hydronium. And then this anion, this is going to convert the water into a hydroxide. We're left with this. And so it turns out that this is quite acidic, but this is more Chem 1b, so we're going to ignore this here. Now, are sodium ions acidic? No. Things like lithium, sodium, potassium, you know, the charge isn't so high. We have to get higher charged species, and then it'll start to turn more acidic. And so we're looking at aluminum 3+ and some of the transition metals, which are quite small. They're going to have a high charge to size ratio. In other words, charge density. And so when we look at the acidity here, the acidities here are given by this. This is a power function. Power function, the lower, the smaller, the more acidic. And so 2.2 would be the most acidic here. So iron 3 is quite acidic. Let's look at aluminum 3 is a 5.0. So iron 3 is more acidic than aluminum. And so it's surprising, these ions, so for example, if you take iron 3 chloride, dissolve it in water, you're going to form an acidic solution here. It has to do with the charge to size ratio. If you look at the charge to size ratio, it's 9.01. 0.19 is fairly high, versus these, like potassium ions, very low, sodium, very low charge to size ratio. And so these aren't very acidic. And so what they did was they tried this. This is what we do in science. What we do is we try to correlate these things with structure. And so here they're trying to correlate the acidity with the charge density of the ion. And you can see, is that a good correlation? It doesn't look like such a great correlation because it looks all over the place. You know, like these. These don't look anything correlated with these. But here, if you look at this cluster here, it looks decently correlated. You know, R squared for this is, R squared is going to be awful for this, right? So if we conveniently ignored these, then do they look pretty well correlated? So maybe we could just sweep these away into the waste bin. You know, I never took that data or something like that, but that's not right, because eventually you're going to have to deal with this here. But what we can see is that, you know, look at the higher the charge density, the more acidic. Well, that only makes sense, because the higher the charge density, the more it's going to suck electron density from the water and make this more acidic, right? Because it's going to be much more polar. Lower charge density, these species are fairly not acidic at all. And so these cations here, so a lot of these cations we wouldn't consider acidic, like, you know, neutral. Sodium ions would be neutral. Sodium ions would be a pK of 14.2 is up here. You know. But when we get to these higher charge density species, you know, 23.2, brilliant. You know, 23.2 is fairly acidic. Now there are other factors that must be in play here, because when you look at the correlation, but what we're trying to do is build things up. And that's it. And so, you know, the same thing, you know, what I was talking about, you know, what we want to do is we want to get a bigger picture of all the structural factors that go in there, and sometimes correlations aren't so clean. And so what we're going to do is we're going to do the acids in the computer lab, and then we're going to correlate that with bond polarity. And then after we do the acids, then we're going to do the amines, you know, ammonia, methylamine, dimethylamine, trimethylamine, and then you're going to look for what the basicity might be correlated with, you know, what structural. And in Spartan, you can analyze, you know, atom by atom for the structure as a whole. All right, are there any questions on that? So I'm going to give you extra time to throw in the ammonia series at the end. Okay, and we're going to go and do that.